Hi everyone, Mr. Boltri here, bringing you video 1.8 on projectiles. So first we're going to talk about why AP loves projectile problems so much. Then we're going to talk about kind of the general approach to solving projectiles problems. And then we're going to run through a quick example. So first, why does AP love projectile problems so much? Because they really do. I was looking through and there are lots of AP problems in the multiple choice, in the FRQ, on projectiles. So why is it that they love it so much? And it comes down to this one fact, that the acceleration of a projectile, just based on how we've defined a projectile, is a 0 in the horizontal direction, meaning it moves with a constant velocity, and negative 10 meters per second squared in the vertical direction, the acceleration due to gravity. So what that means is that in the x direction, the object is moving with a constant velocity. It's experiencing uniform motion. And in the y direction, it's moving with a constant acceleration. It's experiencing uniformly accelerated motion. So that allows AP to ask you questions that involve both of these two really important things that are interconnected at the same time, which it's kind of clear why they really like to test two important things at the same time in a way that is connected. So the question is, how do we approach a projectiles problem when we first see it? So one of the things you're going to want to do is look at it in exactly the same way. Is we're going to split it into the x direction and into the y direction. So then we think about all the variables at play and we just list them all out. So in the x direction, since we have a constant velocity, all we really need is velocity, time, and displacement. But then in the y direction, since we have acceleration, we're going to need a velocity initial and final with that acceleration. So then we list out everything we know, we use our equations to fill in some of the blanks, and then we might get to the point where we're stuck. And the key to this problem is almost always the fact that the object is in the air for a set amount of time. So if we find for the time over here, we can say it's the same as the time over on either side. So being able to move time back and forth between both sides because it's in the air for a set amount of time is often the key to these projectile problems. So first, let's do an example just to kind of solidify what we've been talking about. So if a football is punted on level ground with an initial velocity at a particular angle, how far will the ball go before being caught? So the first thing we're going to want to do always, pretty much with any problem, is just sketch a quick little picture to just help us visualize what it's talking about. So there's a quick little football player. Here you see I've given it an initial height, but it does say it's on level ground. So we're going to say hopefully that it's being caught at the same height that's being kicked. Otherwise, this problem is going to be impossible to solve. So then we just start to break it up and write down any information that we might be able to know from the problem before we start using equations to fill in other information. So it says on level ground, and that means something very important, actually. And then it's asking how far will the ball go before being caught. So what that means is that the change in y is 0. We're assuming it's being kicked and caught at the same height. And then the level ground allows us to say that this delta y, the displacement in the vertical direction, is 0. And so the question is asking, what is the delta x? How far does it go in the x direction? So then what else can we figure out? Well, it doesn't say that it's like on the moon or on Mars or anything. So we can just by default assume that it's on Earth. Should probably say that, but it's kind of a good assumption to say it's on Earth. So then the acceleration is negative 10 meters per second squared. Going back to the problem, we do know the initial velocity and the angle, so we can use what we learned in the last video about vectors and trig to break that into its component vectors in the horizontal direction and the vertical direction. And because of our very nice sketch, we know that the object has more vertical velocity than it has horizontal velocity, because of that 66-degree angle. So when we do the math, we can use that to check ourselves to make sure that we didn't mix up our sine and our cosine. So then we get our initial vertical velocity is bigger than our initial horizontal velocity. Then we can use Pythagorean theorem to make sure that they still, the magnitude of those is still 22.7. Then we have written down everything we can solve from the problem. Then we need to start using equations to solve for the other stuff. So the first thing, it's possible to solve this without finding for final velocity, but if we solve for it, the problem becomes a lot easier. So I'm going to quickly solve for final velocity because I know that this delta x, which really should be delta y, is 0. So it's just final velocity squared equals initial velocity squared. And with these squares, you have to be really careful and think about the direction. So the vertical velocity at the beginning is going up and the vertical velocity at the end is going down. So you just need to add that negative sign on there. But the magnitude is the same because of our handy dandy equation. So then I can just use the velocity, change in velocity equals, acceleration equals change in velocity over change in time equation to solve for the change in time. And then once I have that change in time, I know that the ball was in the air for an equal amount of time in the y direction and the x direction, because we're just talking about the same trajectory for the same ball. So I can just move that change in time over to the left, because that is the change in time for the ball being in the air. So now that I have the velocity and how long it was going for the time, I can just multiply those together and figure out that it went 40.782 meters. And that's going to be the answer to my problem. So just a couple tips when you're approaching these projectile problems. The first is it'll almost always say that you can ignore air resistance, but if it doesn't, it's a fair assumption to say that yes, you can ignore air resistance. The reason for that is that if you can't ignore air resistance, then the path looks a lot more strange, and you'd have to be given a function for what's going on with the path. So for the object to follow like normal projectile procedures with a 0 acceleration in the horizontal direction and -10 acceleration in the vertical direction, we're going to have to ignore air resistance in order to be able to solve that problem. So almost always you're going to be able to do that. Second, is all things being equal, the velocity, the conditions, 45 degrees is going to go the farthest, because higher than that, it's going to get more hang time, but it's not going to go as far because it doesn't have as much horizontal velocity. And shallower than that, it's going to have more horizontal velocity, but it's not going to have enough hang time to go as far. So all things being equal, something that launched at 45 degrees is going to go the farthest. And last but not least, just like with the problem that we just did, if it says that it's on level ground, that's really nice, because that allows us to have some sort of symmetry to the motion. Like the time to go up is going to equal the time to go down. The velocity at the start is going to equal the magnitude of the velocity at the end. So level ground offers symmetry. In most circumstances, we do have to make sure to check that. But oftentimes, if we see level ground, we can celebrate because there's going to be some symmetry to the problem. But also that means that oftentimes we're not going to have something that is landing in the same ground that it started on. So that was just a kind of a quick video on projectiles. In class, we're going to do a lot of projectile problems so we can get really fluent with these, because like I said, AP loves projectile problems. But do let me know if you have any questions, and I'll see you in class. Go Bears!